Today is going to be an awful day for you all. It's going to be an awful day for me too. I am going to spend a considerable amount of time, more than you're comfortable with, answering Ryder's question from Wednesday about why we use complex numbers. So we are going to start by looking at a circuit in the time domain. So I'm going to call this, that is too large. Steady state sinusoidal analysis. In parentheses, time domain. So what we're going to do is we're going to analyze the following circuit. It's going to be pretty straightforward. We have some current source, IS of t, connected in series with some resistance. And let's say that R has a value of 4 ohms. This is in turn connected in series with an inductance. We'll say L is equal to 3 henries. And that's the circuit. That's it. Okay. Our goal is to determine the voltage drop across our current source. So this is going to be our response that we're looking for. Okay. And our constraint here is that this circuit is sinusoidally excited. So I'm going to say arbitrarily that IS is a cosine function that has a magnitude of 2, a angular frequency of 3, and a phase angle of 0, just to make the math slightly more simple. And before we actually start doing any analysis, I want to talk about what our expected result is going to be. Okay. So this is a steady state sinusoidal circuit, which means that it has been operating at steady state conditions for a very long time. Now, it is not a DC steady state condition, it is an AC steady state condition. So effectively, any transient that has existed has long since died out. So in a DC circuit, we saw that at DC steady state, all of our signals were DC signals. At an AC steady state, we should see that, or sinusoidal steady state, we should see that all of our signals are also sinusoids after the transient has died out. And we can bear this out pretty easily in what I'm about to do, okay? So what my expectation here is that my source voltage, Vs of t, will be of the following form. Vm, so it will have some magnitude, cosine 3t. So if we excite our circuit at a particular angular frequency, it seems reasonable that everything will have that same angular frequency. And then some phase angle theta v that will be whatever it needs to be to make this circuit work. And our result will obviously be in volts because we're dealing with a voltage, okay? So that's our goal, is to make our voltage drop across our current source be of that form. We are going to get to an intermediate step pretty easily, but it's not going to be obvious that our voltage will be of that form. And so I'm going to actually plot things on Desmos to show you that it will behave in this fashion. Okay. So we are going to use Kirchhoff's voltage law and write a simple KVL expression here, where we can see that Vs of t is equal to Vr plus VL. Anybody have any problem with that? Vr of t can be determined just by using good old Ohm's law, right? So that's just going to be R times IS of t, which is going to be 4 ohms times 2 ohms. Excuse me, so 4 ohms times 2 amps. So that's going to look like 8 cosine 3t plus 0 degrees volts. And we can say that VL of t is equal to L times the derivative of IS of t. So L in this case is 3 henries. So that's 3 volt seconds per amp. How are we going to take the derivative of 2 cosine 3t plus 0? What's that going to look like? So we can pull the 2 out for sure, right? That's just a constant. So let's pull the 2 amps out, and we're now just trying to find the derivative of cosine of 3t. So what's the derivative of cosine x? Negative sine, okay. Well, using the chain rule, we're going to have to pull out a factor of omega as well, since there is an omega factor that's multiplied by t. So this is going to look like negative 3 per second, because remember that omega is measured in radians per second, and radian is a dimensionless quantity, times the sine of 3t plus 0 degrees. And so we have 3 times 3 is 9 times 2, looks like 18 to me. There's going to be a negative sign out front. So we have amps canceling each other out, seconds canceling per seconds. So the unit of this is going to be volts, which makes sense because this is supposed to be a voltage. I'm just trying to make sure I'm dimensionally accurate. Sine 3t plus 0 degrees volts. Okay, I'm going to put a box around these things for now. So according to our Kirchhoff's voltage law equation, the voltage drop across our inductor, excuse me, the voltage drop across our current source is 8 cosine 3t minus 18 sine 3t volts. Okay. Is that of the same form as what we are expecting? I would argue no. Okay. So we have a sum, or really here a difference of sinusoids, and we are expecting to get a single sinusoid as our output of this system. So I'm going to pull up Desmos. If I can find my mouse, so I'll use the touchscreen. Desmos graphing. So this first thing here, I'm going to call it y1 of x is equal to 8 cosine 3x. That's what it looks like. Okay. y2 of x will be negative 18 sine 3x. That's what it looks like. And I'm going to play with the settings here so we can see both things at the same time. So let's make our y-axis from negative 25 to positive 25. So we see that we have two nice and neat little sinusoids. And what I'm going to do here now is I'm going to add those two things together. So y1 of x plus y2 of x. And now I'm going to turn those things off. So what does this look like? A single sinusoid. So there is a way that we can take that sum of sinusoids and express it as a single sinusoid with a particular magnitude and a particular phase angle. The angular frequency omega will be the same for all of them because that's the frequency at which we are exciting the system, okay? So we are done with the simple part. Now we're going to figure out how the hell we take these two pieces of information and smush them together to make a single sinusoid out of it. And unfortunately, this is wildly tedious. Okay. So I've made our math life slightly easier here by using a phase angle of 0 to start this thing out, okay? So I want to look at a couple of our trig identities that we developed, or didn't really develop, but introduced in the last class, right? So we had trig identity number 5. Let me pull it up here real quick. Was sine alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta. Number 6, cosine alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. Number 7, sine alpha minus beta is equal to sine alpha cosine beta minus cosine alpha sine beta. And the last one that we could possibly use here would be cosine of alpha minus beta is equal to cosine alpha cosine beta plus sine alpha. So I'm going to use one of these 4 trig identities to figure out how to smush this thing together, okay? Anybody have any thoughts on which one I might use? You have a 1 in 4 chance of getting it correct just by blindly guessing. So I'm going to scroll up here. If 3t is alpha and theta v is beta, we have something of the form of cosine alpha plus beta, okay? On the right-hand side of our expression, we have cosine something minus sine something. So I would argue that identity number 6 right here is the winner, because it's going to give us what we want, or it's going to give us an answer in the form we want, and the bits that go into it are already as close as they can possibly be to what we need. So we're going to adapt this very slightly, okay? So I can say that Vm cosine alpha plus beta is equal to Vm multiplied by cosine alpha cosine beta minus sine alpha sine beta, like so. Effectively, I'm just multiplying both sides of that identity by my magnitude. Nothing remotely wrong with that because I've done it to both sides. I'm going to distribute it out a little bit here. So I'm going to have Vm cosine alpha cosine beta minus Vm sine alpha sine beta. Over here on the left, Vm cosine alpha plus beta. All right, so now let's look at what we have, okay? So here for VR, our first term, we have 8 cosine of 3t plus 0 degrees. All right. So I'm trying to think if I want to go that route or not. This could be rewritten as 8 cosine 3t cosine 0 degrees, where cosine of 0 degrees is just 1. And so I can say, actually, let me swap that around. This bit right here is Vm cosine beta. That I can plug in to this expression down here. Okay. Now, this guy right here, I got to think about this for just a moment. I'm so used to doing this with a phase angle that I might have made it harder for me to think about. So that's why I'm trying to figure it out here. All right, let me scratch this off real quick. I know what I'm going to do now. This might take slightly longer, but I'll remember what it is that the hell I'm doing. So if I apply, let's see, so this is cosine alpha plus beta. So if I apply trig identity number 6 right here, I'm going to have cosine alpha cosine beta minus 8 sine of 0 sine of 3t. That's just a more formal description from applying trig identity number 6. Since the sine of 0 degrees is 0, it's the same thing. Over here, I'm going to have negative. So I have 18 sine 3t plus 0. So I'm going to use trig identity number 5. So that's going to be 18 let's see, cosine 0 degrees sine 3t. So that's my 18 sine alpha cosine beta term, where beta is the phase angle thing. And then I'm going to have plus 18 sine 0 degrees cosine 3t, like so. So what I'm going to do now is I'm just going to add these things together. So down here at the bottom, I know that Vs of t is going to be 8 cosine 0 degrees cosine 3t minus 8 sine of 0 degrees sine of 3t. This is all part of the same expression, minus 18 cosine 0 degrees. Sorry, sine 3t. I feel like this is about to give me the exact same result I would have had if I had done none of this, and I'm going to feel like a rascally goofball for doing it, but it'll be okay. And then minus 18 sine 0 degrees cosine 3t. So if I put all this stuff together, this is going to look like 8 cosine 3t minus 0 minus 18 sine 3t minus 0, which, yeah, that did nothing. All right, so sorry, this is frustrating. All right, so that was all a waste of time. Sorry for putting you through it. So effectively, what I'm trying to remember to do here is notes. That'll probably make my life easier. Figuring out how to get the whatchamacallit, the magnitude and the phase angle from this, right? So we have, let's just write it down over here. Vm cosine alpha plus beta, or in this case, it'll be omega t, or excuse me, 3t plus some phase angle theta v is going to be equal to 8 cosine 3t minus 18 sine 3t volts. This 8 right here represents Vm cosine beta. And this 18 right here represents Vm sine beta, if alpha is omega t, okay? So we know what Vm cosine beta is, and we know what VM sine beta is. All right, I've got back to where my brain is working. I apologize for that 8-minute digression of complete and utter bullshit. So we know that 8 volts is VM cosine theta V, and we know that 18 volts is equal to VM sine theta V. So if I had VM cosine theta V squared, which I know I have a numerical value for, and VM sine theta V squared, I can express this as VM squared cosine squared theta V plus VM squared sine squared theta V, or simply VM squared times cosine squared theta V plus sine squared theta V, where cosine squared plus sine squared is 1, right? So from this, I could say that my magnitude, VM, is the square root of VM cosine squared, excuse me, VM cosine theta V squared plus VM sine theta V squared, which is just going to be the square root of 8 volts squared plus 18 volts squared. Get my calculator out real quick here. So the square root of 8 squared plus 18 squared is 2 square root of 97, or 19.698 volts. So that's what I believe our magnitude should be based on the trig identities that we've applied. I'm going to pop back over to Desmos real quick. What's the peak value of this sinusoid? If you can read the graph. Almost 20. So 19.6 and change seems pretty legit. Okay. How do we find out our phase zone? Well, I know that the tangent operation, so the tangent of theta B, should be sine over cosine, right? My stylus will write here. Does it hurt anything if I put a VM out in front of the sine and the cosine function? No, because the VMs just cancel each other out. So from this, I could say that the angle theta V is the inverse tangent of VM sine theta V over VM cosine theta V, which will be the inverse tangent of 18, I believe, over 8. So let's see, inverse tangent of 18 over 8. I get 66.038 degrees. Okay. So from this, I can say that Vs of t is 19.698 cosine 3t plus 66.038 degrees volts. So I'm going to put my keyboard back on my computer, and we're going to see if that matches what we got on our graph. So let's do something down here. So it was 19.6977, so 698 cosine of 3x. Looks like I'm going to be shifting it to the left, so I should have a positive phase angle. Things are looking pretty good. Plus 66.038. And what I'm going to do now, if I close this parentheses, it does not match. The reason it doesn't match is because 66.038 is in degrees, and this is interpreting it as radians. So I'm going to convert it into radians by multiplying by pi over 180, and then I'll be damned, they match perfectly. Okay. So this is how analysis works in the time domain. I flubbed something here, but also like I forgot what the hell I was doing would be a better way of describing it. But I also made the math easier by including a phase angle of 0 degrees from our excitation source. So I would argue that this is a pretty damn tedious process. The math that we did only works for this circuit. So any circuit that we wanted to analyze, we'd have to go through all of this tedious crap again. If we added one more component to this thing, it would be an absolute and utter nightmare to deal with, okay? So now we will address Ryder's thing, Ryder's question. Right? We're going to go back to this intermediate step here. So here is an alternative route. We know that Vs of t was supposed to be 8 cosine of 3t minus 18 sine of 3t volts. That's what we got much earlier on. Okay. I'm going to call this 8 cosine 3t plus 0 degrees minus 18 cosine 3t and so let's see. So if I want a cosine function, I subtract 90 degrees, I believe. Like so. Volts. So these are two sinusoidal functions still. And so we could do trig identities for all of this, but I want you guys to notice something important here. This number is described by its magnitude and its phase angle. This number is described by its magnitude and its phase angle. Polar form complex numbers or exponential form complex numbers are also fully described by their magnitude and phase angle. So I would argue that this is going to be something like 8e to the j 3t plus 0 degrees minus 18 e to the j 3t minus 90 degrees volts. And we can throw that in our calculator or an approximation of it into our calculator using a polar form complex number. So 8 angle 0 minus 18 angle minus 90 degrees. What? Give it to me in polar form, please, because I want a magnitude and a phase angle. And it should have been 8 plus 18 J. 8 angle 0 minus 18 angle negative 90. $19.698 with an angle of does that look familiar? A little bit. We just did that the long way using complex numbers because we had to set up a KVL equation and all of that kind of jazz, okay? So using complex numbers, we can get the exact same result as we would get using all of those terrible trig identities and all of that kind of stuff. Now, I see you guys looking wildly incredulous as to why the hell does this work? This is not magic or sorcery or anything. This is the brainchild of probably one of the most brilliant mathematicians that has ever lived, Euler. So Euler's identity, I introduced it the other day, says that cosine of omega t plus some phase angle theta plus j sine omega t plus some phase angle theta is equal to e to the j omega t plus some phase angle theta. We can arbitrarily scale this by a constant, right? So we could say a cosine omega t plus j a sine omega t is equal to a e to the j omega t. So the magnitude information is carried along as well. So this is what Euler's identity is. Now let's explain why it works using circuits concepts, okay? So if we have, I'm going to bring back the linear black box network, which you guys love so much. So if we have a linear black box network, and we apply some input signal x of t on the left-hand side, could be a current or a voltage. And we measure some response on the output side, y of t. We just showed that if if x of t was of the form x sub m cosine omega t plus theta x, that our output signal y of t would be of the form y sub m cosine omega t plus theta y. That's literally what we just did with that math. We showed that our response will be of the same sinusoidal form, except that the magnitudes can be different and the phase angles can be different. But other than that, they are identical. So if we take this same linear black box network and we apply a very different, or excuse me, a very slightly different input signal. So let's call this X1 and Y1. Sorry for forgetting to do that. So here's X2. And here is Y2. So let's say that X2, we're going to go out on a limb here, is of the form XM sine omega t plus some phase angle theta x. What do we expect our output to be? So if we put a cosine function in, we got a cosine function out. So it stands to reason that if we put a sine function in, we'll get a sine function out. Sorry, this should be a Y. That should be really easy to understand, since we know that sine functions and cosine functions are literally the same thing, just time-shifted versions of each other. So now I'm going to apply one of the properties of linearity, the homogeneity or scaling property. So the homogeneity or scaling property, we learned this in like lecture 5 or 6 or something like that, so it's been well over a month, says that if I scale my input by a certain amount, my output should scale by the same amount. You guys remember that vaguely? Okay. So what I'm going to do is I'm going to scale my input by a factor of j, which in turn will scale my output by a factor of j. Since j is a constant value, there's nothing remotely wrong with me scaling it by this imaginary operator. Now we're going to apply the other principle of superposition, the additivity, or excuse me, the other principle of linearity, the additivity principle, or what you guys commonly know as superposition. If I apply both of these inputs at the same time, excuse me, if I apply both of these inputs individually, it should give me the same output as if I had applied them both at the same time. So if we take our black box network, and I apply just x of t, and I measure just y of t, where x of t is x1 plus x2, I could write this as xm cosine omega t plus theta x plus jxm sine omega t plus theta x, or xm e to the j omega t plus theta x. My output, y of t, is going to be y1 plus y2, or ym cosine omega t plus theta y plus j ym sine omega t plus theta y. And I could obviously convert this into a complex number as well, but I'm going to leave it like this for a very important reason, okay? The real part of our input signal gives us the real part of our output signal. The imaginary part of our input signal gives us the imaginary part of our output signal. So effectively, if we are interested in analyzing a circuit in the time domain, we can represent our sinusoids as complex numbers, do all of the math, and then just throw the imaginary part away because it's not the part that we're looking for. Which is why I can say that this number here, so the real part of 19.698 angle 66.038 degrees is 19.698 cosine 3t plus 66.038 degrees volts, which is what we found earlier. The only thing that's truly missing here is this 3t bit, okay? We had to have known that before in order to put that back in. So to answer your question, Ryder, we use complex numbers because it turns out that the math is astronomically easier if we do it this way, okay? So we are going to now formally, yes, Brody. You don't know. You have to know one or two. We'll have to use it later when we multiply sine functions and all that kind of stuff, but you don't. I wrote them down because they're useful. Your homework is going to make you try to use them. I'm going to show you how to not have to, because I think it's a waste of your time. Okay. So speaking of that, Lucas, if I am not mistaken, you gave me an answer in rectangular form, right? So let's look at something here real quick. The answer that you gave me in rectangular form, I'm still using these approximately signs because we're fudging a couple of very simple things right now that don't actually matter a whole heck of a lot in the long run. But this came out to 18 plus J18 volts, right? The rectangular form, when you do this math, tells you the correct sign for the cosine bit, and it gives you the wrong sign for the sine part. And it's because the trig identity cosine alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. Why that's important, we're taking a tangent here to look at some of your web work. Let's see. Homework 19, I believe, is the awful one. So let's look at this guy right here. We did part of that one the other day. Yeah. So this homework set right here asks you to find the quantity A, B, C, and angle phi if cosine 60 cosine 100t minus 115 degrees minus 39 sine 100t plus 87 degrees was equal to A cosine 100t plus B sine 100t, which is equal to C cosine 100t plus phi. Let's do this real quick for my numbers, okay? I'm going to try to write this down. This is an aside. I just want to illustrate to you how freaking awesome complex numbers are. So we have 60 cosine of 100t minus 115 degrees minus 39 sine 100t plus 87 degrees is equal to A cosine 100t plus B sine 100t. This is also equal to C cosine 100t plus some angle. So the expectation is that you guys will suffer through 45 minutes of trig in order to figure this out. Complex numbers make this entirely unnecessary, okay? So we could write this as 60 cosine 100t minus 115 degrees minus 39 cosine 100t minus 3 degrees because I subtract 90 degrees. This is equal to a cosine 100t plus b sine 100t, or also c cosine 100t plus our phase angle phi. Well, if we treat this as 60 angle negative 115, and we treat this as 39 angle negative 3 degrees, what are we going to get? So 60 angle negative 115 minus 39 angle negative 3 comes out to be negative 64.3036. So let's just round that to 4. Minus J 52.337 in rectangular form, and 89.911 angle negative 140.858 in polar form. This is A. This bit right here minus the, if we throw away the J, is negative B. This bit right here is C. This bit right here is phi. No trig identities needed. Let's prove it. Let's throw it in there into web work. See. So negative 64.304. B should be positive 52.337. C should be 82.910 or 911. And phi should be negative 140.858. No trig involved. 45-minute problem just got knocked down to 2-minute stops because complex numbers are legit. Okay. So Brody, to answer your question, as soon as we're comfortable with complex numbers, we can throw away 97% of the trig identities. Really, the only one that we need to remember is how to convert a sine function to a cosine function. And if we want to get rid of a negative sign, we shift by 180 degrees. Everything past that, complex numbers takes care of. Complex numbers takes care of, sorry. So, all right. So I just gave you guys a wonderful friggin' tool for this homework set for the most part. We do have other stuff that we need to talk about today. So now we are going to more formally talk about circuit analysis in what's called the frequency domain. Okay, so let me scroll up here really quickly. All right, so So let's say that we have a voltage signal V of t that is of the form Vm cosine omega t plus some phase angle theta v, and a current I of t that is of the form Im cosine omega t plus theta I. These are what we call our time domain signals. Now, what I have just shown you guys is what I like to call the mixed domain. So we can say that this is equal to the real part of Vm e to the j omega t plus theta v, and our current waveform is equal to the real part of Im e to the j omega t plus theta I. What we are going to use are frequency domain representations. Okay? So these are specifically called phasors or phase vectors. And how we get from the mixed domain to the phasor or frequency domain is we effectively just throw away the e to the j omega t part. So in the frequency domain, we would have a voltage phasor V with a bar over it, representing that it is a complex number that is simply Vm angle theta V, and we need no other information about it. Similarly, we could have a phasor current I is equal to Im angle theta I, and we don't need anything else whatsoever. Okay. So this is our frequency or phasor domain signals. All currents and voltages will be of this form. They will be described by a magnitude, a phase angle, full stop. Okay. So let's do some simple practice here. Let's say that I have a voltage signal, VA of t, that is 14 cosine 19 pi t plus 113 degrees volts. What would its representation in the frequency domain be? So we keep the magnitude, we keep the phase angle, and we throw everything else away. So 14 angle 113, we're done. What if we had VB was negative 11 cosine 22t plus 55 degrees. We need to get rid of the negative sign because we always want our things expressed as positive amplitudes. So our phasor here, VB, would be positive 11. And then we would subtract 180 degrees from 55. So negative 125 degrees. And we're done. If we had some signal VC of t that was 8 sine 4t plus 12 degrees volts, because the cosine is our basis, we need to convert our sine to our cosine by subtracting 90 degrees. So VC would be 8 angle negative 78 degrees volts. That is how easy it is to convert a time domain voltage or current signal into the frequency domain. We make sure we have a cosine function with a positive amplitude, keep the magnitude, keep the phase angle, throw everything else away. Going back, we just plug the magnitude and phase angle into our cosine function, and we need to know what omega is in order to fill that piece of information is. So going back and forth between the frequency and time domain is very, very trivial, or it's supposed to be very, very trivial, okay? So these are our, how we're representing voltages and currents for this next section of the class, okay? We're gonna be using what are called phasors there. So what I'm going to do now is we are going to develop phasor relationships for our circuit elements. We're going to start circuit elements, sorry, with a resistor. So if I have a resistor like so, that has some resistance R, voltage drop VR of T across it, and a current IR of T flowing through it, then what is my current voltage relationship for this device? Why is it taking so long? Yeah, Ohm's law. V is equal to I times R. Okay. So if we had a time domain signal, V M cosine omega t plus some phase angle theta V, and we had a time domain current signal, IM cosine omega t plus theta I, we could represent this as a mixed domain signal as the real part of Vm e to the j omega t plus theta V. And similarly, our current would be the real part of Im e to the j omega t plus theta I. Let's use that complex number relationship here. So the voltage is Vm e to the j omega t plus theta V. And this will be equal to the resistor value R times our complex representation of our current. Im e to the j omega t plus theta I. So what I'm going to do now is I'm going to split my exponential functions up. So this could be Vm e to the j omega t times e to the j theta V. Everybody okay with that? Breaking that exponential up in that way? And I can break up my exponential on the right-hand side of the equal sign in a similar way. E to the j omega t, e to the j theta I. Noticing that I have a common factor of e to the j omega t on both sides. They cancel each other out. And I'm left with Vm e to the j theta v is equal to r times Im e to the j theta I. So I'm going to make a couple of observations here. I'm going to do these out to the side. The first observation that I can make is that I have an exponential form complex number on the left-hand side and an exponential form complex number on the right-hand side, which means the magnitudes on both sides of the equal sign have to be the same, and the phase angles on both sides of the equal sign have to be the same. So the magnitude of the voltage is just equal to the resistor value times the magnitude of the current, and the phase angle of the voltage has to be equal to the phase angle of the current. If the magnitudes on both sides are equal and the phase angles on both sides are equal, these things must be true. Okay. All right. Now, what this means effectively is that the voltage drop and the current flowing through a resistor will be in phase. There is no phase difference between them. So they're always going to be perfectly matched. All right. Now let's look at the left-hand side of what I've written here again. So I have a complex number that is described completely by its magnitude and its phase angle. Everything else has been thrown away. That is the exact same pieces of information that describes a phasor. So Vm e to the j theta v could be written in polar form as Vm angle theta v r times Im angle theta I, or more succinctly, phasor voltage V is equal to R times phasor current I. So Ohm's law in the frequency domain is just regular ass old Ohm's law. No change whatsoever. So that's a good thing. Okay. Any questions about how resistors behave in the frequency domain? I hope not, because they behave the exact same as they've been behaving this entire time. Okay. Now let's look at what happens with an inductor. So if we have an inductor L over which a voltage drop VL of t occurs and through which a current IL of t occurs, what is the relationship between the current and voltage? And let's use the derivative based relationship so that we don't have to use difficult calculus. Exactly right. VL is equal to L di by dt. So if V of t, actually, I'm not going to write this down again because it's going to get boring. If we're using the same representation of voltage and current that we did in the last example, we could say that on the left-hand side, we have Vm e to the j omega t plus theta v will be equal to L times the derivative with respect to time of Im e to the j omega t plus theta I. So what happens when I take the derivative of Im e to the j omega t plus theta I? I get Im e to the j omega t plus theta I multiplied by j omega. So my derivative operation becomes multiplying by j omega. The integral operation is actually just dividing by j omega. Okay. So I'm going to have Vm e to the j omega t e to the j theta v is equal to j omega L times Im e to the j omega t e to the j theta I. And I can observe that there is a factor of e to the j omega t on both sides that cancel each other out. And so now I've got something interesting happening here, okay? And so what I mean by that is I have a polar form complex number on the left-hand side, Vm e to the j theta v, a polar form complex number on the right-hand side, Im e to the j theta I, but that polar form complex number on the right-hand side is being multiplied by a rectangular form complex number, j omega L, okay? So what I'm going to show you here is effectively what multiplying by j does to a phase angle. So up here in the top right-hand corner, I'm just going to draw a simple graph. This is 0 degrees. Actually, no. This is the real axis. And this is the imaginary axis. So if I go out 1 unit in the positive real direction, what the hell happened here? This is the number we commonly refer to as 1. In rectangular form, this is 1 plus j0. And in polar form, this is 1 angle 0 degrees. If I go out in 1 unit in the imaginary direction, I'm at j, or 0 plus j1, or 1 angle 90 degrees. If I go out 1 unit in the negative real direction, I'm at -1, or -1 plus j0, or 1 angle plus or minus 180 degrees. And lastly, if I go out 1 unit in the negative imaginary direction, this is -j, or 0 minus j1 in rectangular form, or 1 angle -90 degrees. So this j right here is the same thing as me multiplying by 1 angle 90 degrees, which is equal to 1 e to the j 90 degrees. So I could rewrite this bit over here as omega L Im e to the j theta I plus 90 degrees. So multiplying by j means we introduce a positive 90-degree phase shift. So now I have a polar form complex number on the left-hand side and a polar form complex number on the right-hand side, and I can equate the two sides. So we could see that the magnitude of our voltage is going to be omega L times Im, and we can see that the phase angle of our voltage is the phase angle of our current plus 90 degrees. So that means for an inductor, the voltage and current are always 90 degrees out of phase, and the current is lagging the voltage by exactly 90 degrees. All right, so getting back to the left-hand bit of our equation, we have Vm e to the j theta v is equal to j omega L times Im e to the j theta I, which could be written as Vm angle theta v is equal to j omega L times Im angle theta I, or phasor voltage V is equal to j omega L times phasor current I. So that's our current voltage relationship for inductors in the frequency domain. We no longer have to do a derivative. that J. That's the J represents the 90-degree phase shift. All right, so we're going to do this for capacitors now. It's going to be very, very similar to what we just did for inductors. So if we have a capacitor C, over which there's a voltage VC of t, and through which there's a current IC of t. I know you guys are getting bored. We're almost finished. We know that our capacitor current IC of t is equal to C dV by dt. So this is going to look like Im e to the j omega t plus theta I is equal to j omega c Vm e to the j omega t plus theta v, where I just did the exact same derivative relationship that we developed. Taking a derivative is multiplying by j omega. From here, I'm going to suppress my frequency terms. So this is going to give me Im e to the j theta I is equal to j omega c times Vm e to the j theta v, or omega c Vm e to the j theta v plus 90 degrees. So from this, we can see that our current magnitude Im is equal to omega c Vm, and our current phase angle theta I is equal to theta v plus 90 degrees. So for a capacitor, our current and voltage are once again 90 degrees out of phase, but this time our current is leading our voltage by exactly 90 degrees. Okay. Here we have Im angle theta I is equal to j omega c times Vm angle theta v. And so this becomes phasor current I is equal to j omega c times phasor current v. So these are our phasor relationships. Okay. We have one last thing that I want to talk about very briefly, concept of impedance, and then I will be done ranting for the day, and we will be set up for everything we're going to be doing for the remainder of the quarter. Okay. So in DC circuits, the ratio of the current to the voltage is known as the resistance. In AC circuits, the ratio of the phasor voltage to the phasor current is known as impedance. So impedance Z is equal to the ratio of phasor voltage to phasor current. This is inherently a complex number because it is a ratio of complex numbers. So in polar form, we would have Vm angle theta v over Im angle theta I is equal to Vm over Im angle theta v minus theta I, or the magnitude of our impedance and the phase angle of our impedance. In rectangular form, we call this R plus JX, where R is the resistance, and it is the real part of our impedance, and X is the reactance, and it is the imaginary part of our. So we just developed current voltage relationships for all of the elements that we use: resistors, capacitors, and inductors. So the impedance of a resistor is the ratio of the voltage, phasor voltage V to phasor current I. So let me scroll up here real quick. So what happens if I divide both sides of this equation right here by phasor current I? I get my impedance is equal to R. So the impedance of a resistor is simply the resistor value itself. So unexpectedly, resistors behave like resistors because that's all they ever do, okay? So that's our generic form. In rectangular form, this is going to look like R plus J0. And in polar form, this is going to look like R angle 0 degrees. Now let's talk about an inductor. So using the current voltage relationships that we just derived a few moments ago, we'll find that the impedance of an inductor is J omega L, or 0 plus J omega L as a rectangular form complex number, or omega L angle positive 90 degrees as a polar form complex number. And then finally down here, we'll have ZC, also the ratio of phasor voltage to phasor current. And this is going to look like 1 over J omega C, which looks like 0 minus J times 1 over omega C in rectangular form. So 1 over J. Let me just show you guys here real quick. 1 over the square root of -1 times the square root of -1 over the square root of -1 is the square root of -1 over -1, or negative the square root of -1, or negative J. So that's why I can take a J in the denominator and say that it's a negative J in the numerator. So anyway. That is my vet's office. I'll talk to them in a moment. We can also call this 1 over omega C with an angle of negative 90 degrees. Okay. All right. So what are the units of the impedance of a resistor? Ohms. Not a trick question. So the units of the impedance of an inductor is omega, which is radians per second. So per second multiplied by henries, where a henry is a volt second per ampere. So the seconds and the per seconds cancel, and a volt per amp is an ohm. So the impedance of an inductor is also measured in ohms. Let's see what happens with a capacitor. So we have 1 over per second times amp seconds per volts. So the seconds and per seconds cancel each other out. So we have 1 over amps per volt, which is the same as a volt per amp, which we just determined was an ohm. So the units of impedance for capacitors are also in ohms. So if everything is measured in ohms, guess what that means? Impedances combine like resistors. We no longer have to give a shit about memorizing special rules for combining capacitors and inductors and anything like that. Everything gets treated like a resistor, just sometimes they're imaginary. So the math has gotten easier yet again. So what all of this boils down to effectively is that now that we have laid the framework for how circuits are going to behave, because we know how voltages and currents behave, we know how resistors, capacitors, and inductors behave, we can now do analysis in the frequency domain. So I want to work that problem that we worked at the beginning of the class in the frequency domain, and then show you how trivial this is going to be. So here was our circuit. Here was IS of t. we had, if I am not mistaken, a 4 ohm resistor and a, sorry, getting ahead of myself here, a 3 Henry inductor. Let me go all the way back to the beginning to make sure that's right. Yep. Went one too far. And we know that IS of t was of the was 2 cosine 3t plus 0 degrees amps. Okay. So what we're going to do now is we're going to convert. Oh, and we were trying to find this voltage Vs of t. So what we're going to do now is we're going to convert this circuit from the time domain into the frequency domain. So I'm going to redraw my circuit. So I'm going to represent my current IS as a phasor current IS, where IS is going to be equal to what? So how do I get the phasor representation of my current here? 2 angles 0 degrees. Thank you, Zachary. Now I need to convert my other components into the frequency domain. So the impedance of a resistor is the resistor value itself. So our 4 ohm resistor is a 4 ohm resistor. Our 3 Henry inductor is going to be represented by its impedance. So J omega L. So omega is 3 and L is 3. So this is going to look like a J9 ohm impedance. We're trying to find this voltage, Vs, and using Ohm's law, we could say that Vs is equal to 2 angle 0 degrees amps times the impedance 4 ohms plus J9 ohms in series. So throw that in your calculator. 2 angle 0 times 4 plus 9i. And in polar form, we get 19.698 angle 66.038 degrees volts. The exact same result we got using a crap load of trig and other things. In the frequency domain, we get to use all of our DC circuit analysis techniques again. We just have to keep track of complex numbers. Everything that we did in the DC domain. Ohm's law, Kirchhoff's current law, Kirchhoff's voltage law, voltage division, current division, source transformations, Thevenin, Norton, nodal analysis, mesh analysis, all that stuff is fair game. We just use complex numbers. So the next couple of class meetings will literally just be me working an example or two and then asking if you guys what you want to have reviewed. And then we'll do examples that you want just using complex numbers to make sure you're all on board with stuff. All right, so I am done ranting for the day. Sorry, this took an hour and a half. It is better than the 2 hours it usually takes. So that's something. Let me know if you have any questions.